Oh, I don't feel bad for you, Brandon, if you're listening to this. Okay, so we went through on Wednesday some examples, okay? Mainly because James was yelling at me saying I couldn't test you on anything I haven't talked about in class, right, or given anything. So we have some constant strain triangles examples. One is, how do we develop the stiffness matrix? Well, it's really, honestly, it's pretty plug and chug oriented, right? We have our strain displacement matrix. We have our constitutive relationship matrix, which we decide whether we're plane strain or plane stress. We know overall, generally, we're in the plane stress category. Okay, we're going to assume that. And we have some sort of area and thickness associated with this plate. Okay, we know that the thickness is associated with stiffness, right? In the membrane, right? In plane direction. Right? There's no out of plane stiffness in this element. And so I went through and calculated this. Thank you to Daniel and his thoroughness and how, his spring break was. What did you do spring break? Review all my notes? Try to find errors? Is that what you're doing?
Oh, yes, I'm not.
Okay.
I think you just posted this one 2 days ago.
No, this one was posted before the break. You weren't here on Wednesday, that's why.
Yeah.
You weren't here on Wednesday. So Daniel found an error, okay? Thank you, Daniel. In this, okay, this should be 2, 3. All right. 2, 3. Right? Because when we look at this strain displacement matrix, right, this is the partial with respect to y. This is the partial with respect to x. Right? And so all we're doing for the strain direction is we're taking the partial of x and y. And so we just essentially take these values, we're going to plug them in down here, we're going to take these values, we're going to plug them in down here. Okay, so I just transpose those. So it's right at the beginning, right, Daniel, in the earlier notes when we first talked about the CST element? Right in? It's right in the original notes, right?
Yeah,
Just
that's
this
right.
one was messed up. Then similarly, which I'm going to have to dive into this evening, is that you'll notice that in my strain displacement code, I take the first one and minus the third one. Well, it should be the second minus the third.
3 points up. Yeah.
Damn you. I am not perfect, I will tell you that. Thank God for factors of safety. Right? They've saved more lives than we'll ever know, especially that building that the guy fucking designed, okay, and is going back and he took his whole building and let it fall off the side of a cliff, right? Or what's even scarier, and I don't know if I dreamt about it, maybe daydreaming about it over spring break, was the damn barns that they put the plate elements on, right? And that makes those, and you had like 2x6 rafters, right? And so you essentially had like plate. You guys take plates and shells? Is that an option?
It's an option, but I feel like it's not
Really
common.
cool class. Okay, we talk a lot about the field house and how it works and stuff like that, right? It's a big shell. Okay, how an egg, when you grip it, right, in one direction, you can essentially squeeze it as hard as you can and not crack an egg, right? But then you squeeze in the other direction and it cracks really easily. Okay, a lot of cool stuff in that class. I'd recommend it. Do you use it in the real world? Not really. Okay, but it was really cool to learn about. It was really cool to learn about, right? And so with that one scared the shit out of me. But that shit happens, right? And obviously they're still practicing. And so factors of safety, maybe, hopefully, fingers crossed. Scary, okay? But shit happens, all right? So make that change, and I think that is it, right? So on Wednesday, we talked about this already. Just essentially applied the equation, area times thickness, B transpose, our strain displacement matrix times our constitutive relationship. We have to make a decision on what that looks like. And then finally times B again. And I developed a stiffness matrix. There must be some 1, let's see, what did I, it was 1 and 2. Why 1 and 2? That's why. Because y1 and 2 is the exact same value. So that's why the stiffness. Because when I went through my validation here, is the stiffness matrix has to be symmetrical. Right? So if it comes out non-symmetrical, then there's something wrong. Right? And so because my 1 and 2 y coordinates are both 0, when I did 1 minus 3, it's the same as saying 2 minus 3. Okay? So I lucked out, but kind of scary. Right? So this thing should be symmetrical. So that should be the right stiffness matrix. Okay? And I think we ended on that. The next one we started talking about, okay, was what if we have now a CST element, right, constant strain triangle. We have our 3 nodes, and we decide that we now have a material that one has density to it, right, and it's sitting here on planet Earth, so gravity is attached to it, so it's going to have self-weight. Or we're going to say the gravity in this case is acting in the y direction as we normally do. Okay, be careful of that when we start applying that in a finite element software program. Okay. And then finally we have this uniform load that acts on one end of our strain triangle. Okay. This uniform load, as we've talked about, actually I did now that I started talking about this, I think we did talk about this on Wednesday, right? What this load could be from. Could be a wind load that we're applying on the edge of our diaphragm. We decided to simplify our model. For instance, we're not going to model the walls. We're just going to simply apply a tributary width above and below a diaphragm to that diaphragm. So now we have, in this case, this might be on the leeward side of a wind loading case, right? So the wind is sucking on the back side of our building, right? Pulling on it. And so we'd have this load that's pulling away from our element, okay? We could also have, in this case, this is called a traction, right? We also could have, as we talked about in class, a line load. That line load might be coming from a shear wall that's landing on the floor that we're standing on, right? So this, maybe this wall here is a shear wall. So it's getting load from the diaphragm up above or the roof up above that. It's coming down, and maybe this wall is discontinuous. Maybe this wall doesn't extend into the basement, which there's a basement below us, right? So this wall just stops at the floor, doesn't go anymore. So we got to take this load out of this wall somehow, right, and apply it into this wall, into this floor system. And so we might take, instead of a uniform load over an edge, right, perpendicular to the edge, it might be parallel to the edge, right? It might actually start acting in the y direction, okay, and it might just be a line load from nodes 2 to 3. So we would apply that. Would we just do a line load? Is there any other loads you might apply in that case? If we had a shear wall, something like this, okay? Coming down, it has multiple stories above it, right? It's got big shear force acting at the roof and at each diaphragm up above. And then this wall sits on a diaphragm. We would put a line load on that diaphragm. Is there any other loads we might put on that diaphragm that this wall might impose on that diaphragm? Dead load, okay, that would be good, right? Vertical, uniform load along the length. Anything else? You're giving me fingers here, Dawson. What does that mean? Take a guess. This is a safe space, all right? Safe space. No judgment, all right? Until we walk out that door.
Uplift.
Uplift on one end. What about the other end?
Compression.
Right? You're gonna have these big T-C forces too, right? You might do T and C forces if, say, it was maybe a brace frame, right? Because you have these big discrete boundary elements, we might call them, okay? If it's a shear wall, like a concrete shear wall or a wood shear wall, right? We might want to linearly distribute that overturning force, right? So it'd look like, you know, the bending stress in a beam, right? We'd have the maximum stress on the ends, and then it'd be 0 in the center. That might be a little bit more accurate than just saying, okay, we got this big overturning force, we're just gonna have this big T and C force at the end, right? We're gonna have, in our model, that would relate to having, say, a big, you know, concentrated force in our diaphragm that's out of plane, which would start fucking shit up, right? You want something that's more uniform than that. Okay? So in this example, though, we've got, say, our wind load, and we have our dead load of our plate. And so from that, we would need to know, well, what's the thickness of our plate? Got our 1/2 inch. We'd also need to know the density of our plate, right, for gravity. In this case, if we were using steel, that density would be 2.84 times 10 to the negative 4 kips per cubic inch, or what's the weight of steel in pounds per cubic foot? 490 pounds per cubic foot, okay? So previously in the CST element, we talked about our equivalent nodal forces. Well, when we have forces on our CST element, we're allowed to have surface tractions, right? When we're talking about surface forces, we have forces that act over an area, right? So we have the integral of our shape function, right, times our magnitude of these tractions, right, which would be phi x, phi y. Tractions in the x and y direction. And then finally we have body forces, right? And we talked about how body forces are really over the entire volume, okay? In our case, if we have self-weight, that's a density related thing that is related to the volume of our element. So we really have now a traction and a body force, okay? So we have this problem has an applied uniform load along the edge on 2 to 3 and the self-weight of the plate. So if we start by just looking at the uniform load, now I'm going to need to start writing stuff in there. We have our integral, right, over the area of our shape functions times our tractions, okay? If we look at our uniform load, similar to the equivalent forces we just did in the homework, right? So we had a point load and a uniform load, right? And we evaluated that point load and the uniform load, okay, based on their overall contribution over the entire element, okay? A uniform load acted over the entire length, right? So we had the integral, we had to sum up essentially all of its individual contributions. And as you all got from that homework, the point load is essentially a uniform load just at one discrete point, right? And so you could just evaluate the shape functions at that given point. So with that concept in mind, what do you think what would be your uniform load contribution? What would this integral become, right? You have the integral over the area, this traction force times our shape functions, right? And the integral over the area. We have this uniform load now that's acting just on the end of our plate. Any ideas what the integral now becomes? Integral over the area. It's similar to the point load, right? Our point load problem, we didn't have variation in one of the coordinates. For our beam, our coordinate is just the x coordinate, right? For our plate, now we have two coordinates. So we could have a surface traction that is essentially a uniform load over the full surface, right? But in this problem, we just have a uniform load that acts between these two nodes, right?
So the name is dy, that's what's there.
Yeah, so it varies with respect to dy, but it doesn't vary with respect to x, right? And more importantly, in the x direction, it's acting at a specific x, right? And so our integral now becomes that, right? It has a known magnitude, right? That's our dx, right? Known magnitude, 0.1 kips per inch. Our shape function, well, that magnitude, it doesn't vary over the x direction, okay? And so our shape function needs to be evaluated at that location over which that uniform load acts. Well, it acts at x equal to 2, right? It acts along this edge where our x equals to 2. So that'll give us what are our contributions along that line of that uniform load, okay? And what we know from shape functions, right? If we had a uniform load that acts along this line, what does N1 equal? 0. More confidence, Madison. 0, right? And more importantly, what's the sum of N1, N2, and N3? What should it equal? 1, right? So N2 evaluated at x equal to 2, and N3 evaluated at x equal to 2 should equal 1, if everything is appropriate. So our integral becomes that. right? 0 to 3 being that we're going from y equals 0 to y equal to 3. We're going along the full length of that edge with respect to y. Well, I'm going to pull out our constant here, kips per inch, integral 0 to 3 nt x equal to 2 dy, right? And as you guys did in the homework, very straightforward, right? So if we talked about what n1, n2, and n3 would be. Well, if we evaluate our shape functions at x equal to 2, okay? These are our shape functions. If we went back to our CST notes, these are our shape functions, right? We end up getting n1 equal to 1 minus 1/2 x. Well, that is 0. That's a good thing, right? If the loads are only acting along the line that is between nodes 2 and 3, we shouldn't have any forces that come from those applied loads that act at n1. Or similarly, right, these are essentially the keys that give us the relationship of what's going on in the field to what's going on at the nodes, right? Whether we start at the node and we're trying to figure out what's going on in the field, or we have something going on in the field like our loads, and we figure out what's going on at the nodes, right? And this relates to compatibility. We've talked about that before, right? In one of the homeworks, I think it's homework 2. We talked about the fact that if we're going along the line between 2 and 3, in order to have compatibility with, say, the next element, right? If we decided to model another element that kept going beyond to the right of this, okay? We better hope that n1 has nothing to do with what's going on along this line, right? Because otherwise, that n1 that's out here is going to also influence what's going on along this line. And now this line is no longer going to be sitting together between these two elements, right? So it's a big compatibility thing. So that's good. We got 0. If we evaluate n2, we get 1 minus 1/3 y, and then we get 1/3 y. We sum those together, right? All three of them, right? 0, 1 minus 1/3 y, plus 1/3 y. We get 1. That's also good, right? I want to make sure that we're always going to be equal to 1. All right. So if we evaluate this, we're going to end up with, right, n transpose, that's just n2 and n3. We're going to get 3/2. If we take the integral, which is 0.15 kips and 0.15 kips. Which is really just tributary width, right? We take our uniform load and we're just going to put it at our 2 locations. Right, we don't have moments. Right? We don't have rotational degrees of freedom in this CST element. So these are really just translational forces, right? Forces in the x direction at nodes 2 and 3, which relate to just taking our 2 uniform loads. Any questions about that one?
So that's just the loading node, like, do you ever have, I guess with the CST, do you have moments that get transferred to those nodes based on like interior loading, like with a beam?
You will,
element?
you would if the element itself has the degrees of freedom to allow for rotations, right? It's taking into account rotations. But this element has no ability to track rotation or moments, right? Forces at our nodes. The degrees of freedom for this is just translation in the x and the y, no rotation. And so if you look at our force vector, it's just R1, right, in the x direction, R1 in the y direction, R2, R3.
That's the constant strain triangle that is that way? Or
No,
is this-
that's our overall F equals KD equation, right? Because our degree of freedom, our D matrix for our CST, right, is really just the displacements translationally at our 3 nodes. So that it can only move this way or this way.
Just for the way we are evaluating it.
That's all
Yeah,
based
right.
on how we developed
Just-
this plate element. That all came from saying, okay, we are going to develop a plate element. It has 3 nodes. We're gonna give it 2 degrees of freedom at each node. And when we only give it 2 degrees of freedom at each node, right, and it's only able to translate, right, the force, we only are able to give it a translational force, right, which would just be a point load in the 2 directions. So we looked at our force vector for this. It's just gonna be F1x, F1y, right? No rotational things. So when we put a uniform load on it, that uniform load, the equivalent forces that we create can only be translational forces. We can't put a moment on it. We're gonna talk in a little bit, it'll probably be Wednesday based on how long this thing's taken. It's called the Ullmann triangle, and in VA, that's the element that VA uses, and that element has what we would call a drilling degree of freedom, or essentially, you can have both translation, X and Y, and rotation of this node, okay? Which, with the axis of rotation being out of the page, that's why they call it a drilling degree of freedom, so it can rotate. And in that case, then yeah, you have a moment, right? That is essentially a torque on each one of these nodes. And if that's the case, then you end up getting 6 shape functions, and those 6 shape functions, 3 of which relate to the rotations of these. And then you would have a moment contribution due to
From
this.
that.
Heavy, right? Riveting. Aaron, you look so excited to be here today.
I'm really, really excited to be here.
I bet. How was Tennessee?
It was really, I got a lot of sleep, and, no, I'm kidding. It was
Okay,
really good.
I was gonna say, like, you went there where are you from again?
I'm from Montana.
Yeah, so like, what's going on in Tennessee?
I have a buddy that went to school with here that moved back, and we were musky fishing all week,
Oh, nice.
unsuccessfully,
Oh,
but it was good.
but you drank a lot.
Wow, didn't sleep a lot.
Oh, okay.
A lot of time fishing.
Oh, nice, good. Well, hopefully you can gain a little more sleep in this class. Be ready for Wednesday. Okay, so that's why the moment isn't there, Elias, right? Because the derivation of this element doesn't have that as a degree of freedom, and if we don't have that degree of freedom, we won't have that energy equivalent load.
So anyone who ever uses the constant strain triangle won't ever have
Won't ever have it, ever, okay?
Got it.
But if they use the Ullmann triangle, which is a different plate derivation, which is what is used in VA, then yes, you would have a moment attached to, you'd have a force in the 2 directions, plus you'd have a rotational moment that would act at the node,
Always.
always. Okay. You might not have an energy equivalent moment if the loading was such that it didn't have a moment, right? If you had like a series of, say, 10 of these triangles, right, and like vertically, right, we just kept, say we flipped this one this way, and we took this whole thing, we flipped it, and we just copied it up, and you ran this uniform load over the whole length, right? Symmetry would tell you that the loading attached to something here with uniform load equal on both sides, that it's not gonna wanna rotate this node, right? In that case, the energy equivalent moment on this node is gonna be 0. Right? But on the end nodes, it wouldn't be. Yeah, good discussion. Man, you guys are coming back. It was real slow at first, but I think you're really picking it up. This is good. Okay, now we have self-weight, right? Which is really just essentially the same thing, except for now we're adding another coordinate. We're going to say it's in the z direction, okay, because it's over the volume. And if it's over the volume, well, we know the thickness is constant, right, in the z direction. So we can pull that out. And we know that we have its density, right, which is going to provide us with an actual force, right? So we're going to have density times thickness. And then we have the integral over the area. So I just plugged in, right, density, thickness, multiplied those two together, okay? And at this point, this is when we would integrate, right? And in a software program, you have to integrate numerically, right? For, I think pretty much everyone was here. Well, you two guys weren't here on Friday, right? Adam talked about the idea that when you create a model, right, and the program is developing a stiffness matrix, right? That program, in order to come up with that stiffness matrix, for instance, right? For a CST element, for instance, right? So we're talking very simple plate element. Careful. We've got all of these multiplications that need to happen, right? All of these processes that go into just developing the stiffness matrix of one element. You might have 1,000 of these elements, right? This guy gets really, really big. You got a lot of adding, multiplication, maybe you take it to powers, right? A lot of numerical, right, operations that are happening. And in doing such, a computer is limited to 16 bits, right? You can essentially go out to 16 decimal places and then it stops. Well, in going through the process of multiplying, dividing, taking it to powers, you might have, right, it might not be perfectly zero. And so what he was talking about on Friday was the fact that you might have a model that runs, but in reality it's unstable. You might run it a second time and it becomes unstable. And that's because the nuances associated with all of those operations that are compounding over and over and over again might give it a chance to have some amount of stiffness, right, when it should be zero. And might allow numerically, right, in the program, we can take the inverse of this, right? It's not singular, so we can take the inverse of it. And so you would get an answer out. It might be a terrible answer, like the example that Adam showed was what was the nickname for the guy? Astronaut, right? Because his model deflected 7 light years, right? Because you're gonna get an answer. But because that stiffness is very, 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 very small, so it might be 0.00000001, right? And that 1 came from the fact that we were doing multiple operations of this stiffness and we didn't end up getting it to perfect 0, right? Because when you divide 3 by 4 or something like that, right? It's on for so long and you don't get an exact answer and you do that multiple times. So you're gonna have this very, very small stiffness and then all of a sudden, boom, it comes out and you get a real displacement, well not a real displacement, but you get a displacement, right? And in that case it was 7 light years out there.
It also rotated like millions.
Yes, and it rotated 1,000,000 times, right? And so you can get an answer. It might not be a good answer, but you can get an answer, which comes back to validation, right? So there's error in just the numerical operations of our programs, right? Of our software systems. And that's where we can, right? For the body force, just for self-weight. If we modeled a plate in VA, and it was this dimension, say in inches, okay? And it had a certain load associated with it, in order to figure out what the energy equivalent nodal forces are of that self-weight, visual analysis would have to take the integral of it, right? And to do that, they do numerical integration. And to do numerical integration, it's essentially it's a time step thing, right? You guess the solution, you come back, you're kind of trying to converge to a solution, or a final solution, right? And when it does that, you actually end up getting additional errors, right? Because again, it's limited by 16 bits, so you're not going to get an exact answer. You're also not integrating exactly, okay, symbolically like we're going to do in a second, okay? So we end up getting what's called error due to truncation. The solution might have 100 decimal places out there, right? And we're only able to capture 16 of them. On top of that, we can't integrate exactly. Okay, we integrate numerically, which we're essentially bounding the solution. We're guessing on either end. Okay, and there's different methods to do that. I'm not sure what visual analysis uses to do that, but they integrate numerically, and so there's sources of error, right? So that's the big thing there, is that there can be sources of error associated with integrating. Okay? But if we go through and we do it symbolically, this is simple enough, right? We have the integral over the area of our shape functions, right? Evaluated over, right, our x and y domain. Okay, so we start with our shape function 1. We go from 0 to 2 and 0 to 3.5x. We end up, this whole thing equals 1. Next one, integrate over the volume. This one equals 1. Anyone guess what the last one is?
1.
Woo! Got it. See, I'm not gonna trick you. 1. What's the area of this thing? How many square inches is the area?
What?
How many square inches is the area, Aaron?
2 times 3 square inches.
Nice. Crushed it. 3 square inches. And at each node, we have 1 square inch. Makes sense, right? Kind of tributary width to each one of our nodes. So we have A over 3.
It's not an equilateral triangle though, so kind of, I don't know. They each.
But you're thinking your tributary area goes halfway to each of the adjacent nodes, right?
I feel like it would if you had equal lengths, like from the center of gravity
But
to
if you-
each node, then you would, but this one, the
But if you looked at, if we
bottom
just,
right node is
but if
closer
we
to
looked
the
at just
center.
one of these, each one of these, right? We're gonna go the tributary width, just like we had with our uniform line load, right? We took half to each side, so we essentially take half to each side, okay?
Right.
And when we do that, in the end, we end up getting half, or a third. We essentially get a third of the area that contributes to our body force at each one of the nodes. I get what you're saying. Like if you got like a really thin, long, super short triangle, but what ends up happening is you end up still getting a third of the area because you're going to still go halfway. Like if you just evaluate, if you look at it as like a traction force and you're looking at just the line between them, you're going halfway between each one. If that makes any sense.
That's where you start getting some weird aspect ratios though.
Yes, which isn't good from a modeling standpoint, but we can talk about that in convergence and stuff. Okay, so we get 1, 1, 1, and 1, 1, 1, and 1, sorry. 3 1s, multiply it out, negative 1.42, negative 1.42, negative 1.42. And like we did in the homework, right? We would have a total energy equivalent force vector. This force vector is really what's going on at node 1 in the x and y directions, right? No moments, we just have translational forces because that's how the CST element is derived, right? No rotations, just translations. And so we end up adding these together. We have 0, negative 1.42 times 10 to the negative 4th. We have 0.15, right? We had the force in the x direction at node 2. Wow, this is really squishing this, and I don't need to. So we have negative 1.42 times 10 to the negative 4th. We have 0.15. We have negative 1.42 times 10 to the negative 4th. 0.15. And negative 1.42 times 10 to negative 4th, right? So that would be our force vector. And we would plug that in, right? F equals KD. And we would then impose boundary conditions. Well, what's going on at those two nodes? And once we have boundary conditions, then we can come back and we're going to calculate what our displacements are, right? Once we partition, we're going to have unknown displacements. Once we get those displacements, we're going to combine our entire displacement vector again, right? And then now we have the stiffness matrix, the original one. We'd multiply that out and we get all the forces, right? Just like we did in the homework.
Can we go back to the test equation?
Which one?
Let's keep going. Right
This-
there.
Yeah.
I believe at the previous equation, is that summation of those two equations, so there's a GAO. Is it the integral of the area, is it dA or like that?
Saying on your first.
Oh, yeah. It would be over the area, right? Yes, Daniel, for sure. Man, you were on it. All right, any questions? Okay, well, we will plan on an exam on Monday. give it to you in class, we'll go over it just briefly. It'll be due Wednesday, end of day. No cheating. What else? I think that's it. We'll finish the rest of kind of what I would call the theory here on Wednesday and Friday. And then Monday we'll start with digital analysis. Dawson, you were great. Decided not to show today?